yesterday we were discussing, we just started discussing quantum error correction, and in particular, let me remind you that we were yesterday's lecture we were discussing the general theory of quantum error correcting codes. So today, what the plan for today is to finish that up and then talk about applications to AdS CFT. But before we do that, let me just quickly begin by reminding you what we were doing yesterday. So remember that from our discussion yesterday, the general structure of a quantum error correcting code is that we have a subspace, which we often call the code subspace, which lives inside a bigger Hilbert space, which I will denote as the physical Hilbert space. And you want to protect the information contained in the code subspace against some errors that happen here on the bigger physical Hilbert space. We model these errors by the action of a quantum channel, which we also talked about yesterday. And we say that this code, namely this code subspace, is a subspace of the physical Hilbert space. This code can protect against a particular error channel E, provided there exists a recovery channel R, which can reverse the action of the error only on the states supported in the code subspace. So namely, R, there exists an R such that R of E of rho equals rho when rho belongs to, or when rho has support on the code subspace. Okay, that is important. This condition is not true for all rho, but only for those density matrices which have support on the code subspace, which is to say that we can protect the logical information that is contained in the code subspace.
Hi, Onkar.
Yes.
Yeah. Can you just qualify what you mean by the redundant coding? Just at the beginning of your slide.
Yeah.
You say that it is coded redundantly. What exactly do you mean?
In the quantum, so in the classical context, this makes sense, because in the classical context, what you do is that you just take one bit and you sort of copy it on several bits. So that is where the word redundantly comes in. But here, I mean, in the quantum context, I perhaps should put this word redundant in quotes. It's supposed to mean that you're taking a small amount of information and you're sort of smearing it out in a very large Hilbert space, the physical Hilbert space, in such a way that it's protected against erasure of error. That's essentially what I mean. Another way to say this is that, for instance, in the context of quantum, the erasure codes that we are going to look at later in the context of AdS CFT, for instance, what that means is that you don't need the entire physical Hilbert space to encode the logical information that you're encoding. If there is if you delete some part of it or you erase some part of it, then a much smaller factor of the physical Hilbert space is needed to decode the logical information. So in that sense, you can think of this as redundant encoding. But I mean, the word is not strictly to be thought of. I mean, it's not like we are copying the same information over and over again, because that's not allowed by quantum mechanics. So yeah.
Okay. Why I was asking this question is that I mean, I'm a little bit confused as to whether the way you code the Hilbert space, the smaller Hilbert space and the larger Hilbert space, does it have an effect on whether there's a existence of a recovery channel or not? I mean, this is why I'm asking this.
It does. Yes, exactly. It does. So it matters what the encoding is. So in particular, which subspace of the physical Hilbert space you're looking at will determine what kind of error channels it is protected against. And you can see this very explicitly in this Neal-Laflamme conditions, right? So towards the end of yesterday's lecture, we discussed that the existence of a recovery channel is equivalent to this condition, right? We haven't proved this completely, but I was just giving you some intuition for it yesterday. In this condition, you can see it quite explicitly, because not only are the Krauss operators for the error channel making an appearance here, but importantly, the code subspace projector is also making an important appearance, right? So depending on what code subspace, yeah. So thank you for that question. Yeah. Any other questions? Okay. So okay, so good. We were discussing yesterday that what it means for a quantum error correcting code to protect against the error channel E is that you must have an recovery channel R, which will reverse the action of the error channel. And there is a very nice set of conditions which just makes this checkable, if you like. You can just check whether an error channel can be recovered from. And these are the so-called Neal-Laflamme conditions right here. P here is the projector onto the code subspace. The EM and ENs are Krauss operators for the error channel in question. And one important thing here is that this matrix alpha, which are just numbers, just coefficients, but this matrix of coefficients alpha mn has to be Hermitian. Okay, and we discussed yesterday that the physical interpretation of these conditions is that firstly, the Krauss operator of the error channel must preserve the structure of the code subspace, namely it should map orthogonal vectors to orthogonal vectors. And secondly, different Krauss operators, there exists a basis of Krauss operators such that different Krauss operators map the code subspace into different orthogonal subspaces inside the bigger Hilbert space. So this is the picture that one has in mind. Different Krauss operators, let's say F1 and F2 and F3 and so on, where F is a suitable choice of Krauss operator for the same error channel, will map the code subspace into different subspaces of the bigger physical Hilbert space, but importantly, these are all orthogonal to each other. Okay. And okay, so then we were just discussing how to go about proving this theorem. So what we said was, we said, so the part of the proof that I will go through in detail is the part where you assume the Neal-Laflamme conditions and show that the existence of the recovery channel. This I find most insightful and enlightening, so I'll go through this part of the proof. The reverse assertion, which is that if recovery is possible, then Neal-Laflamme conditions are satisfied, is much. I don't find it very enlightening, so I won't go through that part of the proof. But you should, as an exercise, do that for yourself. But you can find this proof, of course, in Nielsen and Schwab. So the way the proof goes is that you first use the fact that this matrix alpha is Hermitian to diagonalize it, to find that there exists some unitary matrix U such that you can can diagonalize alpha. You then use this unitary matrix to construct a different set of Krauss operators for the same error channel. So remember that these FNs here, these are a different set of Krauss operators for the same error channel. And we discussed this yesterday. When you do this kind of an operation on the Krauss operators, you get back the same error channel or same quantum channel. Okay. And now, so think of these FNs just as a convenient set of Krauss operators for the error channel. It's the same error channel, let me emphasize. They're sort of convenient because they diagonalize these Neal-Laflamme conditions. So, if you compute P, FM dagger, FM P, where P again is the code subspace projector, then you can just substitute this formula here for the FNs, and then use the Neal-Laflamme condition for the E's, the Krauss operator representation E. So that's this step over here. And then alpha was chosen to diagonalize, sorry, the U's were chosen to diagonalize alpha, so that a quick calculation will show you that what happens is that the Neal-Laflamme condition in terms of these F Krauss operators, or this F basis of Krauss operators, becomes diagonal. Okay, it's this. So it's just a convenient representation for the error channel in terms of which these Neal-Laflamme conditions get diagonalized. So in a sense, these FNs are nicer Krauss operators. But so then what you do is that for each one of these FKs, so now we are always going to work with these F Krauss operators. For each one of these FKs, you consider the action of these FK and the code subspace. So we ask how does this Krauss operator FK act on the code subspace, So that's another way to do that is just compute fk times the code subspace projector. And using this polar decomposition theorem, which lets you write any operator as a unitary operator times square root of a dagger a, where a is the operator you began with, you can show, sorry if I'm going a bit quickly, I'm just reviewing what we did towards the end of last lecture. But do ask any questions if you have. So this fk times p, you can using polar decomposition write in this form. So here uk is some unitary operator, and here this thing here is square root of fkp dagger fkp. So now using the Néel-Laflamme conditions inside the square root gives you tells you that this thing here inside the square root is proportional to the code subspace projector. So that's this, and there's some number. There's a number sitting out front, which is the element of the diagonal matrix. But that number is not going to concern us too much. So that's square root of gk. This is just a number which is sitting out front. But what we learn is that the action of fk on the code subspace projector is to basically rotate it. Okay, there is a unitary matrix uk which acts on the code subspace projector, so it just rotates this projector into a different projector. Okay, and in particular, what that different projector is this one. So the boxed equation here. The new projector pk, or the projector, so this pk is a projector on the new code subspace, the image of the code subspace under the action of fk. Okay, and it's nothing but a rotation of the initial code subspace. And using this little manipulation here, we can write this projector onto the new the image of the code subspace as 1 over square root of this number times fk p uk dagger. Okay, that's a simple manipulation. Just substitute this ukp I've substituted with fkp divided by the square root of d. Now, the important thing here is that these.
Hi, Onkar, can I ask?
Hi.
Yes, I missed what UK was. What was?
Yeah, UK was, so what we did was we took this, so we wanted to ask how this fk acts on the code subspace.
Yeah.
So we took fkp and we did polar decomposition on it. So in other words, we wrote it as a unitary operator times square root of something, this square root of this positive operator. And that unitary operator I'm calling uk.
Okay, thanks a lot.
Yeah.
So Onkar, does all these orthogonal components, like which are obtained by projector pk, they all qualify as code subspaces also?
They are images of the original code subspace.
Right, but as you said, there's a recovery channel for the original code subspace.
Yes.
Would this imply that for all these subspaces obtained by projector pk, they will also be recoverable somehow? I mean,
against the action of which?
Against the action of your epsilon. Oh, but that was only defined on the original subspace. I see. So code subspace is still the same one. These ones.
Yes.
Okay.
Yes, exactly. Yes, exactly.
Just a clarification.
Yes.
So this equation that you have written, the topmost FKP equation.
Yes.
This defines what UK is for you, right?
Yes,
UK is
exactly.
not something arbitrary.
Exactly.
Okay.
Exactly. So there is unique polar decomposition. So FKP is given by this. So there is some UK which satisfies this equation. Right. I don't know what that is, but there exists the UK.
Right. So because you have chosen the positive definite metric, this defines for you the UK.
This defines UK. Yes, exactly. Okay. Thanks for the questions. So then so what this accomplishes is that we have all these projectors PKs now, which are nothing but projectors onto the images of the code subspace under the action of various Krauss operators. And basically the Néel-Laflamme conditions say that these are all orthogonal projectors. So you can do a very simple computation, which I think we did at the end of your last lecture, where you can just compute PL times PK. That is the overlap between two of these image subspaces, and you find using this equation that they are all orthogonal. Okay, so in particular, PL times PK is 0. This again is one of the main contents of the Neal-Laflamme condition. Okay. So this is where we stopped last time. So once you realize that the images of the code subspace under different Krauss operators are orthogonal, then that gives you a strategy for how to recover from this error. The strategy is very simple. What you do is I want to construct a recovery channel that will reverse the action of the error. So what one does is, first thing, you project on these PKs. Okay, I want to. So you can think of this in two steps. You first project onto a PK. This is to check whether a particular error happened or not. So you can think of this projection on PK as checking whether the kth Krauss operator, the error corresponding to the kth Krauss operator happened or not. And if it did happen, you can simply rotate back to the original code subspace by doing UK dagger, right? Because remember that the action of the kth Krauss operator on the code subspace just rotated it by this UK to a new subspace in the full Hilbert space. And if that had happened, you can just rotate back by doing UK dagger. Okay. The problem here that could have occurred is that if these different images were not orthogonal to each other, then you wouldn't be able to tell which error happened, right? Because projecting on it could be that there is overlap between these different subspaces, and then it's not possible to distinguish whether F1 happened or F2 happened or F3 happened and so on. The Neal-Laflamme conditions basically say that because all of these Fs map you into different orthogonal subspaces, you can always tell which kind of error happened and then rotate back. Okay, that's the basic intuition behind this formula. But nevertheless, that's just intuition. The way you write the recovery channel is this. Okay, you take, so I have to tell you how this recovery channel acts on the general density matrix sigma. You plug the sigma in here, you project it onto these kth subspaces, these images of the code subspace under the kth Krauss operator, and then you rotate back by these UK. Okay. Good. Now let me call this thing here, this thing inside this bracket.
Sorry, Onkar,
yes,
what is the ... the plus?
Yes, I'm coming to that. Yes, okay. I'm going to come to this ... in one moment. Yes, okay. Thank you. Yeah. Yes. So let me call let me call this thing here. I want to call it RK. And this thing here is RK dagger. Okay. So these RKs and these RKs that we've defined, namely, so RK is just UK dagger PK. Okay. This you can think of as like as a Krauss operator for the recovery channel. Remember from last time's discussion, we said that you can give the action of a channel by just specifying its Krauss operator, right? So think of, what I'm giving you here is I'm giving you the Krauss operators. I'm giving you the Krauss operators for the recovery channel. Okay. So the claim is that the Krauss operators for the recovery channel look like this. Okay. And you can easily convince yourself that if I compute RK dagger RK, then you're going to get this thing here. Just this is a simple thing. And because U is a unitary operator, this becomes PK. Okay. So in particular, if you do the sum over K, RK dagger RK, you're going to get the sum over PKs. Okay. And that may not span the entire physical Hilbert space. That's some projector, right? Sum over K PK is some projector. So if you want the R to be an honest recovery channel which preserves trace, then you have to just add to this formula here the orthogonal complement of that projector. So Gautam, this is I'm trying to address the question you asked. So basically, this what these dots here are is add to this formula the orthogonal so you just write 1 minus sum over K.
I see.
sigma 1 minus sum over k pk. Okay.
I can ask a question about, so the K is labeled the H environment, right? As a, because the K index K itself, right?
Yes. Yes.
So, I mean, naively, could I think that the environmental Hilbert space has larger cardinality than the system Hilbert space, and so PK will always,
you might have
the sum over PK will give you a.
You might have thought that, but you could also have, so the first situation is where the environment naively, so you can also consider situations where the environment is very small, first of all.
Okay. So,
right?
for
that
you
is,
need this extra.
yes, exactly. So this is for that situation. If the environment is sufficiently large dimensional such that this orthogonal complement 1 minus sum over k pk is 0, then that's great, because then you don't need to add this.
Okay, thank you.
Thanks for the question. And great.
Another thing is that the recovery somehow should be kind of an inverse process to the error, in the sense that you are trying to undo the error.
Yes.
So are you going to discuss some?
Yes.
Okay, good.
Yes. So exactly. The intuition, Gautam, is just this, that exactly. So the intuition is that, what the way this error acts, the way Fk acts on P, on the code subspace, is that it just rotates P by this unitary operator UK. So intuitively, all you have to do is, okay, this formula is getting a bit cluttered, but all you have to do is check whether the kth error happened and then rotate back. Okay, that is the intuition. So check, project onto the kth image and then rotate it back. That is intuitively why this recovery you would expect to work. Okay, and importantly in that statement is the fact that these PKs are all orthogonal. If they were not orthogonal, then this wouldn't make sense. But because they are orthogonal, at least intuitively, I hope that it's clear that this could, you might hope that this works, right?
Got it.
Yeah. And so that's the intuition. But more explicitly, you can just check it. So now I've given you a formula for this recovery channel. This is the formula. Okay, this is the formula. So then you just check it. You compute R of E of rho. Right? You compute R of E of rho. That is by definition just RK, so this thing here inside with the sum over L. So let me write the sum over L inside. This thing here is the action of the error channel on rho. And this thing here, the sum over K, RK dagger, that is the action of the recovery channel. Right? And now it's a simple exercise. You just plug in the formula. So I told you that RK was UK dagger PK, RK dagger was this thing here, PK UK. Now in this formula, note that I've dropped the ... terms, and that is because the ... terms are that is the projector onto the orthogonal complement, which is killed by the fact that this thing, that is killed here, right? Because these FKs, is this clear? The ... dots were orthogonal to all these image subspaces.
Yeah.
Okay. So those terms are exactly drop out in this part. Okay. And then now it's a matter of just calculation. So now you just, here going from here to here, all I've done is I've inserted P's because rho was a density matrix supported on the code subspace. That's all that I've done going from here to here. Then going from here to here, the next line, you substitute your formula for the PKs. Okay, we have a formula for the PKs in terms of the FKs. So you just substitute that. And then you use Néel-Laflamme conditions. That you just keep using Néel-Laflamme. First of all, these UK dagger UKs go away. Then you can use Néel-Laflamme condition here, and you can use the Néel-Laflamme condition here. And what you end up with is this particular thing here. So what this is sum over K D, these diagonal entries times rho. So what you've done here is that you've shown that R of E of rho is some number times rho. But actually, you can also check that this thing here is 1, provided E is trace preserved. Okay, that's a simple exercise that you can check by just taking the trace of the Neal-Leplan condition. Okay, so I'll leave that for you to check. This number out front is actually 1, so that means that R of E of rho is exactly equal. Okay, so what we have shown here is that if the Neal-Leplan conditions are satisfied by the quantum error correcting code, then there exists a recovery channel. And this is a very constructive proof because I'm giving you explicitly what this recovery channel looks like. It's this.
Onkar, can I ask a question about the small u? The small u. Yeah, the small u. So the quantum channel itself, the E, the epsilon.
Yes.
That dependent on the state that pollute, like the psi naught that you used in lecture 1 of the environment that polluted your.
Okay. Yes.
And on the unitary that mixed the physics.
Yes.
And
yes.
so small u depends on both. I just wanted to check on.
Wait, what was small u, please?
Small this one.
This one.
When you did polar decomposition, and
yes.
the u, right, as in the proof. Yeah, I guess this one, right.
Is it this one, the where we took this alpha matrix and we diagonalized it? Is that what you mean?
That one, or no, sorry, the one that I guess is the same one. Then the proof, when you did the polar decomposition.
So that is a different u. So
yeah,
this is not small u. This is I meant to write this as big u. Yeah, but okay. Yeah. So what was your question, please?
So this u depends on both the unitary that mixed the environmental state and the system state, and also on the psi naught, the state that polluted. Like
yes.
Depends on both, right? It depends on both.
Yes. Exactly. Yes. I mean, I don't know whether there's anything clean I can say about like what part of the U.
Okay, yeah. But it will depend. I mean, if you change
in
one
general,
of them, it will change, presumably.
In general, yes, exactly. Okay, so that proves the Neal-Leplan condition. So what this proves is that if the Neal-Leplan conditions are satisfied, then there exists a recovery channel. And I wanted to go through this part of the proof because it's a very constructive proof. It just gives you the recovery channel on the nose. So now, if you know that there is an error channel which satisfies the Neal-Leplan conditions, you can just explicitly write down the recovery channel. Okay. You can also prove the other statement the other way, which is to say that if recovery is possible, then it must be the case that this quantum error correcting code satisfies the Neal-Leplan condition. Okay, it's also not very hard, but let me actually leave that to you to either prove by yourself or check or look up the proof in Nielsen and Chuang, because it's not, in my opinion, very enlightening. So I wanted to move on to other things in order to get as quickly as possible to AdS. Okay, any questions before we move on?
No questions in the chat, Onkar.
Okay, great. Thank you, Nirmal. So let's move on. So now what we've done is we've come up with this general criterion for when a quantum error correcting code can protect against the action of some error channel E. Okay, these are these Neal-Leplan conditions. So I wanted to, before we move on to AdS CFT, then that's the agenda, of course. But before we move on to that, it is helpful to recast these Neal-Leplan conditions in a slightly more information-y way, if you like. And this thing goes under the name of the decoupling principle. Okay, so the decoupling principle is just another way to state the Neal-Leplan condition. It's just another completely equivalent way of stating the Neal-Leplan conditions in a more, if you like, an even more accessible and information theoretic way. Okay, so the way this goes is the follows. Again, I'll state it as a theorem and I'll go through the proof, at least try to give you the intuition for the proof. Okay, good. So let me introduce these basis states I. These I's are a basis states for the code subspace. So remember that the structure of my quantum error correcting code is that there is a code subspace inside the bigger physical Hilbert space. And these I's are going to be a basis for the code subspace. Okay. Now, let's say E is my error channel. And what I'm going to do is I'm going to introduce a set of basis vectors, EMs, for the environment corresponding to this error channel. Okay. Remember that we can think of this error channel as coupling the physical system to some environment and then doing a joint unitary operation and then tracing out the environment. We can always do that. And I'm going to introduce some basis vectors for the environment Hilbert space. We're going to call them EMs. And you can think of these EMs as corresponding to these Krauss operators, capital EM. Okay, so remember that we discussed that the Krauss operators, capital EMs, are like EM, the joint unitary U corresponding to the error channel, acting on some initial state psi naught on the environment. That was how they are related. So what one does is one introduces, now I understand that this thing is getting a little bit cumbersome, the notation is getting cumbersome, but I have to introduce one more element. So I introduce a reference Hilbert space. Okay, this reference Hilbert space, what it is, I know that this might feel like unnecessary complication at this stage, but it really makes things much nicer. So let me do this one thing. So let me introduce this reference Hilbert space. What this reference Hilbert space is that it's isomorphic to the code subspace. Okay, so if you had a qubit, let's say that you were trying to encode in this larger Hilbert space, then the reference system would be another qubit. Okay. Now, once I do that, I define a state. Okay, I define a state capital psi, which is the maximally entangled state between the reference and the code subspace. So this thing here is just, so actually I don't need to write this. Let me just write this as. Okay, so these I's, remember, are a set of basis vectors for the code subspace. The reference Hilbert space is completely isomorphic to the code subspace, so I can use the same basis if you like. And what I'm doing here is I'm writing down the maximally entangled state between the reference and the code. Okay, there is an environment factor that's sitting around, but it's completely decoupled. So this is one state. This is one state, and then the environment is just sitting on its own. Okay, it's not doing anything right now. Okay, so think of this as this. What you're doing is you're preparing a maximally entangled state on your code subspace. You know, this is sort of the state before interactions with the environment. Okay. Now, what happens? So the idea of this decoupling theorem is to ask what happens to the state capital psi when the physical system starts interacting with the environment. So, in other words, the error channel acts on this state capital psi. Okay. So let's call the new state psi prime. So psi prime is the state where, you know, this joint unitary U has acted on the physical on you know the physical and the environment factors. Right? Remember that the way this error channel acts is that you bring in this environment in some initial auxiliary state E naught, and then you couple the physical system to the environment by the action of this joint unitary transformation, right? So that's my new state psi prime. Okay. Equivalently, you can write this state in terms of the Krauss operator, because these Krauss operators are precisely defined to be the overlap of UE. So remember this formula here. Where is it? Yeah. So the Krauss operators were defined as that. So using this expression, you can simply check that this state psi prime can be written in terms of the Krauss operators like so. Okay, so it's the mth Krauss operator acting on the physical factor, and then this thing here becomes EM.
Onkar,
Is this clear?
yes. Hi, Onkar.
Yes. Hi, sir.
So is the physical Hilbert space the same dimension as the code subspace, because you're using the same eyes to?
Yeah, it's a bit confusing, but the code subspace is much smaller than the physical Hilbert space. So I was just, so maybe let me use better notation. Sorry. Okay, good. So I'll use the following notation. So the eyes are a set of basis states for the code subspace. So span of eyes is the code subspace. And then let me call psi eyes in the physical Hilbert space. Let me call them the images of, so these are like the, the image of the code subspace. Is this clear? So the code subspace is the subspace inside the physical Hilbert space, right? So yes. I'm just calling the corresponding vectors in the physical Hilbert space psi.
Okay, thanks.
Yeah, so let me use that notation just to avoid any confusion. So let me. Is the notation clear? I hope that this hasn't caused any confusion. So psi eyes are just like the, the code subspace is a subspace inside the physical Hilbert space. And I'm just introducing a basis for that subspace, and I'm calling them psi eyes.
So that's the map of, that's this the embedding map of I into
exactly. Yeah. Exactly. So you can think of this formally as, having some isometric map between the code subspace to the physical Hilbert space. And you can think of the psi eyes as
V of I.
Exactly.
The other question is that you are using two symbols for the dimension. One is capital N and the other is little d.
Oh, I'm so sorry. So sorry about that. Yeah, there's just only one d. Yeah.
So little d is the dimension of the code subspace.
Code subspace. Exactly.
Okay.
Sorry about that. Okay. So a little bit of an information explosion happened. So what we did was we introduced this maximally entangled state on the code subspace psi, and then we acted on the state with the error. Okay, the new state is now psi prime. Psi prime is this action of the error operation on the maximally entangled state on the code subspace. Okay, and this is the expression for it. Now the claim is that this error channel E is correctable if and only if the reduced, so you take this new state psi prime, namely the action of the error on the maximally entangled state on the code subspace, and you compute its reduced density matrix on the reference and the environment subfactor. Okay, this state psi prime has three factors in it. It has reference, it has the physical system, of course, and then it has this environment factor. Okay, you ask, what is the reduced density matrix between the reference and the environment factors? And the claim is that the error is correctable if and only if this reduced density matrix factorizes. In other words, the reference system, which was maximally entangled with the code subspace, is completely decorrelated from the environment after the action of the errors. Okay, in physical terms, the environment that corresponds to the error gets no information about this reference system. Okay, it's completely decorrelated from. One way to say this, a different way to say this, is that the mutual information between the reference and the environment in the state psi prime is 0. Okay, and the claim of the theorem is that this condition is completely equivalent to the Néel-Leclerc condition. Okay, so the reason that I find this, first of all, this connects up directly with the Ryuta-Kainagi formula, as we'll see in a few minutes. But I also find it much more useful in a sense, because it tells you what to compute. You compute one number, namely this particular mutual information here, And if that number is 0, then you're guaranteed that the error channel can be recovered. Okay, or the quantum error correcting code will protect against the action of that particular error.
But Onkar, you still have to construct R to recover. That would
yes, you absolutely. You have to construct R to recover, and for that you have to go back to the discussion we've already had. But if you just wanted to check whether this error can be, And the other thing is that, as we'll see in a few minutes, this is directly related to the root channel.
So in the previous characterization, checking if it's recoverable and finding a recovery channel, they were kind of tied together.
Tied together.
Here now you have like
they're slightly decoupled. Yes.
Decoupled. Okay.
Yeah. Thanks for the question. Okay. So
hi, Onkar.
Onkar, sorry. Why is this story equivalent to the Neil-Laflamme?
Yes. So that's that's the next thing. We'll prove that. Yeah.
Thanks.
Yeah. Any other questions?
Hi, Onkar. I have a question.
Hi. Yes.
Yeah. Hello.
Yes. I can hear you.
Right. I'm a little confused by the factorization condition. Can you please go back to that?
Yes.
Of the density matrix?
Yeah.
So on the left hand side, you have done a partial trace over the reference system and the environment, right? And
sorry. I'm so sorry. That is just my bad. So let me define it. So the definition of this thing is that you trace over everything else. So you trace, in particular, you trace over the physical system.
Oh, okay.
Yeah. So you trace out the physical system, you get the reduced density matrix on reference and environment. And so similarly, this thing is also defined similarly. This thing here would be, for instance, trace over physical system and the environment system. Is this clear?
Yeah.
Okay.
Yeah, because I was a little confused that after you traced over the reference and the environment, how does it occur on the right side?
Yes. Sorry.
Okay,
that's just notation. Yeah. Thanks for the clarification. Great. Okay, so this is a completely, as I was saying, completely equivalent reformulation of the Neil-Laflamme conditions. And the way to prove this is, can you guys hear me? Because I'm getting a message saying my internet is unstable.
Yeah. It's no problem so far.
No problem, right? Okay, just let me know if there is any.
Yeah.
Okay, good. So the proof goes as follows. So let's first assume that the channel E is recoverable. And then we'll show that the mutual information. Okay. So if the channel is recoverable, then we know that the Neil-Laflamme conditions are satisfied. Okay, this was the content of the previous theorem. We didn't quite prove this in the previous part, but it's true. Okay. So so that means we know that the Neil-Laflamme conditions are true. Now all you have to do is just compute. You just compute this reduced density matrix on the reference and the environment system. So that is, by definition, that is this thing. It's the trace over the physical Hilbert space of this guy. And it's just the computation. So you take this formula for psi prime. So we have an explicit formula for psi prime here. This one. Okay, and you just plug it in. You plug it into here. When you do that, what you will learn is that I'm using an old notation. What you will get is this. Okay, this I hope is clear. All that has happened is that we have traced over the physical part of the Hilbert space. So the physical factor has gotten converted into a number, a correlation, this particular correlation function, and everything else is as it is. But here we can use the Neil-Laflamme conditions because both psi I and psi j are elements of the code subspace. So in other words, I can just introduce this projector for free. So here we are in business because this is just the Neil-Laflamme conditions tell us that this is just alpha mn times delta ij. So plugging that in this equation, you manifestly see that this thing is factored. Okay, so it's some matrix, some density matrix on the reference and some density matrix on the environment, and they don't talk to each other. Okay. So that part of the proof is very simple. Okay, you just compute. You just compute, and the Néel-Laflamme conditions tell you that the density matrices have to factorize in this. Okay, so the Néel-Laflamme conditions directly tell you that there has to be no correlation between the environment and the reference system. Now, the other part of the proof, so okay, so this automatically implies that the mutual information is 0. In particular, because the mutual information, I mean, this is a fact, but it is true that the mutual information is 0 if and only if the density matrix is factored. Okay. Now, going the other way, I have to show that if the density matrices factorize in this way, the density matrix on ref environment factorizes in this way, then it must be the case that Néel-Laflamme conditions are satisfied. So the way to prove that is the following. Again, this is not very hard. So what you do is you think of the state psi prime. So psi prime, of course, is a state which lives in this Hilbert space. It has 3 factors: physical, reference, and environment. Now, if you just focus, so what we are told the assertion is that the density matrix on the reference and environment system is factorized. What we can do is we can take that density matrix and we can write a purification for that density matrix. Okay, I'm going to call this purification psi star. The way I'm going to do it is I'm going to just double it. So the density matrix looks like there's some okay, so let me explain what I've done here. So I can always write rho prime on reference and environment as sum over, let me call these two labels I and M, Pi QM I on the reference times M on the environment. Okay, this assertion is only true in writing this formula. I've assumed that this density matrix factorizes between reference and environment. Okay, if it didn't factorize between reference and environment, this would not be true. What I would have to write is something like this. Okay, so the more general statement is that this density matrix looks like some, let me use a I comma M lambda I comma M I comma M I comma M. This is the most general thing. Any density matrix, of course, I can write in this way, but I'm further using the fact that I'm told that this density matrix factorizes between the reference and the environment, and that allows me to specialize to this case, right? In particular, these eigenvectors factorize into I tensor M, and more importantly, that's sort of trivial, but more importantly, the eigenvalues factor. Okay, so I'm crucially using here the fact that I'm told that this density matrix rho prime is factorized between the reference and the environment. Now, once I know that, I can write a purification for this density matrix rho prime, which I'm going to call psi star. And what psi star is it's like the thermophile double construction. You take the density matrix and you just write it as a pure state on the doubled Hilbert. Okay, so take these I's and you copy them on a new system, which I'm calling reference star, like the double version of the reference, and then environment gets its own double copy, the environment star. Okay, so this thing here is a purification, a particular purification, which is sometimes called the canonical purification of the original density matrix rho prime on reference and environment. Okay. But now note that reference environment density matrix came from tracing out the physical Hilbert space in psi prime, the original state psi prime. Yes. So you now have two different purifications of the same density matrix. One was psi prime, the other was psi star, the psi star that we just constructed. Okay. When you have two different purifications of the same density matrix on reference environment, they ought to be related to each other by a unitary transformation acting on the other side. So here the unitary transformation doesn't act on reference environment, but it only acts on reference star environment star, namely, it only acts on this other side, this double copy. It does nothing on the reference environment part. It only acts on the double copy of it. Okay, so this has to be true because these two states are two purifications of the same density. Okay, and now it's a simple yes.
Yeah. So can you just remind us what was psi prime and how is it a purification?
Yeah. So one second. So let me go back. So psi, remember that psi, we did this in two steps. Psi was the maximally entangled state on the code subspace. This one. And psi prime was the action of the error channel on that state. Okay, so what I did was I acted with this joint unitary operator acting on the physical and the environment Hilbert spaces, and equivalently I can write that in terms of the Krauss operator like this. So this is psi prime.
Okay, so you're taking the action of this channel is like a purification, rather.
The action of the, so remember that the way the channel acts, you can think of as bringing in some environment and doing a joint unitary transfer, right? That's what I'm using here. So the error acts by bringing in this environment and then acting on the physical and the environment Hilbert spaces with this joint unitary operator U. The second line here is just another way to write that same formula in terms of Krauss operator. Is this clear? I may have misunderstood you.
Okay. No, I mean, how is this a purification? That's what is confusing me. Maybe it's
okay.
like we can.
Good. Okay, good. Okay, now I understand your question. So this is psi prime. Okay, so let me first say that this is psi prime. Now, what I did was I computed the reduced density matrix of psi prime on reference and environment. Right, that was the density matrix we were talking about. So clearly psi prime, so
right,
this rho prime came from tracing out the physical part, the physical factor in psi prime. Psi prime was a pure state, but I traced out the physical sub factor in psi prime and I got rho prime. So therefore psi prime is a purification of this density. Is this clear? So that's all I mean.
Okay.
So
yeah.
When I say it's a purification, I mean that it's a pure state, which when I trace out some factor of, I get rho prime.
Okay, thank you.
Great. Thanks. Yeah, thanks for the clarification. So psi, in that sense, psi prime was a purification of this density matrix, and psi star was another purification of that density, just by construction. Okay, and when you have two purifications of the same density matrix, they're related in this way. Okay, now it becomes a simple matter to check the Néel-Laflamme conditions, because the Néel-Laflamme conditions, the thing that you need to check is this guy. It's very simple. It's a simple algebraic thing to show that this object is just simply this. It's a particular matrix element inside psi prime, the state capital psi prime. And if you just plug this formula into here, I won't go through the algebra. It's a matter of simple algebra. You just plug this formula into here, and you will end up concluding that this is proportional to alpha mn delta. Okay. It's an interesting exercise to do, though, because you will learn what these alpha mn's are when you do that. Okay, you learn that the alpha MNs are basically overlaps between the. It's interesting. It's a nice exercise to do. There are two sets of basis vectors on the environment that we've introduced in this discussion. One was this this eigenvectors of this rho prime that forms a set of basis vectors on the environment, or it gives you a set of vectors. May not be a full basis, but some set of vectors on the environment, subspace for the environment. There is another basis of vectors, which was this EMs that you started off. And these alpha MNs are related to their overlaps. Okay. So it's a very nice exercise to just convince yourself that that this is true, and that then get a formula for the alpha M. Okay. I'll leave that to you as an exercise, but I hope that at least the spirit of the proof is clear. If this was a bit technical,
Sorry, I think.
Yeah.
yeah.
He's back.
Yes. Hello.
No. We lost you for like few seconds.
Okay.
Just 2 seconds.
2 seconds. Okay. Sorry. So I was just trying to recap what we have accomplished here, even if the proof was technical and maybe not too fast to follow right now. What we have accomplished is that we've come up with an information theoretic criterion to check when an error is recoverable. What you do is you write the maximally entangled state on the code. You introduce a reference system. You write the maximally entangled state between the reference and the code subspace. You act on that with the error channel that defines psi prime. And then in that new state, you compute the reduced density matrix of the state on reference and environment. And if that density matrix factorizes between reference and environment, the error can be recovered again, or the error is protected. Or in other words, we have to compute one number. We have to compute this mutual information in psi prime between reference and environment. Okay, that's what we've accomplished. So that is all that I want to talk about in terms of the general theory of quantum error correction. I wanted to say a few words about the singleton bound and so on, but I think I'll in the interest of time, I'll skip that, and I'll now go to AdS CFT. But before we do that, any questions about the discussion so far?
Nothing in the chat, Onkar.
Questions. Onkar, maybe you can share your notes later.
I will, absolutely. I will do that. So there are some more things in the notes, but I'll skip them. Yeah. Great. Okay, so then let's move on. In the last the last remaining half an hour or so of these lectures, let me move on to the thing that we actually wanted to get to, which is the application of all of this formalism to AdS CFT. So this often goes under the name of entanglement wedge reconstruction. And a nice reference, I think, one of the early papers which explained this in a very nice way was this paper by Daniel Harlow. And there are also other papers by Dong, Wall, and Harlow, and so on. Okay. So in the AdS CFT context, the code subspace is the set of states in the CFT which we can interpret from the bulk point of view as semi-classical states, namely, some states where there's a fixed bulk geometry, and then there are some quantum field theory excitations living on that geometry. Okay. So in this context, there is a very clear, code subspace or code subspace kind of structure which emerges. Namely, there is this bulk QFT Hilbert space. This bulk QFT Hilbert space is just the Hilbert space of quantum field theory excitations on a fixed bulk geometry. So let's say you have some AdS and you have some scalar fields on top of AdS. This is fixed AdS and like excitations of the scalar field on top of AdS. So think of it that way. On the other hand, there is a much larger Hilbert space, namely the CFT Hilbert space. The CFT Hilbert space has all kinds of states in it. It has black holes and so on. Nevertheless, we can think of the bulk QFT Hilbert space as living inside the CFT Hilbert space by the AdS CFT map. So this map, which sends the bulk QFT states into the CFT Hilbert space, is essentially the AdS CFT map. Okay. So in that sense, the bulk QFT states can be thought of as a code subspace, or more precisely, the set of states in the CFT which can be interpreted from the bulk point of view as some QFT excitations on a fixed geometry, can be thought of as a quantum error, can be thought of as a code subspace inside the CFT. Okay. Now we want to view this subspace as a quantum error correcting code. In other words, the claim is that this subspace inside the CFT has some nice properties against, the action of a certain class of errors. And what are these errors? So in order to explain what these errors are, let me just remind you what the Ryu-Takayanagi formula says. So the Ryu-Takayanagi formula is the following statement. If you have, so here what I'm drawing is I'm drawing a constant time slice. So let's imagine a t = 0 slice of the bulk geometry. Okay. So the circle here, this circle here is the asymptotic boundary of AdS. We can partition that asymptotic boundary, let's say, into two regions, A and A bar. Then the Ryu-Takayanagi formula says that, first of all, it says that the entanglement entropy of A, capital A, is given by you find the minimal area surface, or more precisely, what you do is you define this quantity, area over 4g Newton plus S bulk, over all possible surfaces that are anchored to this boundary subregion, and then you find the minimal one. In our context, where we are only going to think about leading order corrections in G Newton, you can think of the surface as the minimal area surface that is anchored to the boundary of the boundary side. Okay, and then the entanglement entropy is, of course, A over 4g Newton. But importantly, there's also this correction term coming from bulk entanglement, which is often called the FLM correction, which says that we have to include in this boundary entanglement entropy a piece coming from the bulk entanglement entropy for this shaded region. This shaded region here is called the entanglement wedge. Okay, it's the region between the minimal surface and the boundary subregion capital A. This I'm assuming most of you are familiar with, but just so that everybody is on the same page. If there are any questions, please do ask. Great. Now, the claim is that if this code subspace, in other words, if we are considering, okay, so let me just say one more thing. The code subspace is, we are free to consider the code subspace to be sort of any subspace of the bulk QFT. In particular, it's not, I mean, I don't necessarily want to consider the entire bulk QFT Hilbert space. I can just isolate a mode, let's say let's say some scalar field in the bulk. I can construct a wave packet using that scalar field, and I can focus on that, on the excitations of that wave packet. Okay, so imagine that I construct like a simple harmonic oscillator, degree of freedom, by using some wave packet mode of this bulk scalar field. I can think of that as my code subspace. Okay, I ignore all the other QFT excitations in the bulk. I just want to focus on the excitations of this one particular mode in the bulk, and I'm perfectly within my rights to do that. So that's what I'm going to do in this discussion, because that makes life much simpler. So I'm going to think of just as a simplification of this problem, I'm going to think of H code as excitations of one such mode. Okay, is this clear? I hope that this is not going to cause any confusion.
Yeah, I think so. But Onkar, you just draw it in the shaded region for convenience. You just want to look at one
I
mode.
could have constructed this mode here as well. Yes.
Yeah. Okay.
So there are two possible cases. I could have drawn it in the shaded region or in the non-shaded.
Okay.
Yeah. So the code subspace, as I say, I emphasize is in this discussion, I'm going to just consider one mode in the bulk, and its excitations are going to label the code subspace. Okay. Now the claim is sort of easy to state. The claim is that if this wave packet that I considered, if that was in the entanglement wedge of capital A, then this code subspace is protected against the erasure of A bar. Okay, that is the claim of quantum error correction. So I gave you a subspace inside the CFT Hilbert space. The subspace was the set of states which corresponded to excitations of this one particular mode. The claim is that if this mode was in the entanglement wedge of capital A, then this subspace is protected against the erasure of A bar.
Sorry, I'm a bit confused about what it means to say it's contained in this region. If I consider a momentum mode, it'll be everywhere, right? For instance.
That's right. So I'm considering a very special kind of code subspace where this I'm constructing this code subspace as excitations of a particular wave packet mode, and this wave packet mode is chosen such that it's sufficiently localized. Either you can take it to be localized in the shaded region, the entanglement wedge of A, or you can choose it to be localized in the entanglement wedge of A bar.
So you're not allowing arbitrary high fluctuations of
exactly. So these are special kinds of code subspaces that I'm focusing on.
Onkar, what is the scale of localization that you have in mind?
It's basically much. I mean, you know, so the scale of localization will of course affect. Yeah, I mean, it's basically the QFT cutoff, right? You want to like localize this mode will be localized at the scale of the QFT cutoff, and you just want this QFT cutoff to be much smaller than AdS length, for instance.
Okay, I see.
Yeah.
Much smaller than I see. So you're in the momentum space. It's very high. Maybe this is what Sujay was asking also.
Yes. So there is some cutoff, so which is like 1 over the QFT cutoff, and I just want, so this is essentially the scale of localization of this mode, and you know, or in other words, the scale of localization is more precisely the sort of frequency, what kind of frequency I'm using for this wave packet. I just want that to be much smaller than the LADS.
Right. Okay. Good.
Yeah. So in other words, I'm considering a wave packet mode, which is sufficiently localized inside in the entanglement wedge, so that it's sufficiently localized with respect to the, let's say, AdS length.
Yeah. Thank you.
Yeah. Good. So now.
Onkar, so but also not probably too localized, right? Because you want I mean, this lambda QFT also sets the dimension of the code subspace in some sense, right? Because you want it to be finite dimensional, your Hilbert spaces. Is it correct that you can think of this as lattice field theories with cutoff given by lambda QFT and
right? But here the code subspace that I'm considering are just excitations of this one mode, right? It's like a simple harmonic oscillator and its excitation. So if I wanted, I could just take the first the zero ground state and the first excitation.
Right, but I'm saying that's, as you said, that is for an example. But like if I just want to look at like a scalar field in AdS and apply the quantum error correction ideas, because it's a EFT, that means that there's a UE cutoff, and that gives me the somehow dimension of the Hilbert space that I work with, right? Like is that correct to?
That's roughly true, but yeah, I mean, I think that I mean, you know, you can try to formulate it in the bulk QFT language, and I think that some of these things are better formulated in that case in an algebraic setting.
Yeah.
So,
but the algebra, I was thinking that should be finite dimensional because many of the results that as you were showing, they apply for finite dimensional Hilbert spaces. So somehow, it is true for field theory.
Or you work directly at large n. So in the infinite n.
Yeah. Okay.
In the infinite n limit, you can do this in an honest way in the bulk UFT. But if you want to do it at finite n, then yes, I agree.
But Onkar, sorry, even at infinite n, I mean, if I just look at the like a scalar field theory, like naively, I would have thought that, of course, scalar field theory has Hilbert space is infinite dimensional. But because I have a IR cutoff of the AdS scale, and if I put a UE cutoff, then it's like a lattice theory with finite dimensional Hilbert space, which is where these ideas would really apply. And
if you put a cutoff in the bulk, lattice cutoff in the bulk, you say?
Yeah, because I'm saying we have to put a cutoff because we are ignoring gravity. So I'm saying that we are anyway, otherwise back reaction would anyway make gravity dynamical. I was just trying to see whether
But back reaction is controlled by G Newton, right?
G Newton, exactly.
Yeah. So so you're saying you only have to consider states where the energy density is not comparable to 1 over G.
Yeah, and I'm saying that whatever cutoff it is, it will make the number of degrees of freedom finite in the end, because there is some cutoff. UE cutoff, there's already IR cutoff, and then ideas will directly apply the error correcting ideas. I mean, it's a large Hilbert space. It's not, but it's finite dimensional.
Sure. I mean, yeah, if you put cutoffs and stuff, yeah, sure, you can probably also make it work. I mean, that effectively makes the problem finite dimensional.
Right, exactly.
So in order to avoid all of those confusions, I'm just going to focus on one particular mode and consider the excitations of that mode. So then it becomes manifestly like a finite dimensional.
Onkar, one question: If
yes.
Is it enough that this excitation is localized in a small region compared to the AdS scale, or should it be small compared to the size of the wedge that you are choosing?
Yeah, I mean that's the size of the wedge is comparable to AdS scale, right? Because
I could choose like a very small wedge. There's no.
Right. Okay. That's true. Yeah, I wasn't considering those situations. Yeah, sure. I mean, it basically has to be separated from it. It has to be far from the entanglement cut, sufficiently far from the entanglement.
Right.
Yeah. So in other words, it has to be well localized within the wedge. I think you're right. Any other questions? Okay. So as we were discussing. So in this particular setup of a subspace inside the CFT Hilbert space, which consists of the excitations of this one mode, which is either well localized in the entanglement wedge of A, or that is the shaded region, or in the complement of that region, you can make a clear statement about its quantum error correction property. Namely, this mode is protected against the erasure of, if this mode was well localized in the entanglement wedge of capital A, then it is protected against the erasure of A bar. Okay, that is the statement of that is sort of the quantum error correction structure of this code. And now it's not very hard to check this. So we've already built a lot of the machinery required to check this. So let me quickly show you how this works. So this statement actually just follows from the decoupling principle that we discussed a little bit ago. The kind of error I want to consider is I want to consider the erasure of A bar, right? Now, if you remember the erasure of A bar, or the trace over A bar, partial trace over A bar, we discussed this in the last class. You can think of partial tracing over A bar as basically bringing in an environment subsystem which is isomorphic to A bar and doing a swap operation. Okay. In other words, so what I want to compute to check for these for this error correction criterion is I want to compute the mutual information between the reference and the environment systems, as we discussed. But in the current setting, and the environment system is just another copy of A bar, and all I'm going to do is the joint unitary is just going to swap the environment with the A bar. So instead of computing this, I might as well compute reference with A bar in the original maximally entangled state on the code subspace. Now there's no prime here. So the psi is just the maximally entangled state on the code subspace. There's some reference, and then that's maximally entangled with the code subspace. Is the statement clear? Let me just repeat it once in case it's not clear. So what we ideally want to do is we want to bring in this reference system, maximally entangle it with the code subspace, do this joint unitary transformation on the physical and the environment subfactors, and then compute the mutual information between reference and environment. I'm claiming that in the current situation where we just want to trace out A bar, this is equivalent to just computing the mutual information between reference and A bar on the maximally entangled state on the code subspace. This is because the environment you can think of as just another copy of A bar, and the joint unitary that you have to do just swaps the state on environment and A bar. We discussed this in the last lecture. So therefore, all you have to do is the calculation on the left-hand side is completely equivalent to computing the mutual information between reference and A bar on the original maximally entangled state on the code subspace. Okay, so that's what I want to compute then. I want to write down this maximally entangled state on the code subspace. So here it is. This is the maximally entangled state on the code subspace. And I just want to compute in this state the mutual information between reference and A bar. Okay, this is a simple computation. So the definition of this mutual information is that it is entanglement entropy of reference, entanglement entropy of A bar, minus actually the entanglement entropy of reference union A bar. This is the definition of the mutual information. But because this state psi is pure on reference A bar, this thing is the same as the entanglement entropy of A. So I might as well just compute the entanglement entropy of A here. Okay. Now, this quantity here, the entanglement entropy of the reference system, is just log D, because the state was maximally entangled between reference and the physical Hilbert space, or the CFT Hilbert space. So the reduced density matrix on the reference part will just be maximally mixed. Therefore, its entanglement entropy will be log D. Okay. Now, the thing that we really need to compute are the entanglement entropies of A and A bar in this particular state. What is the state? The picture is this. There is this wave packet or this mode in the bulk whose excitations constitute the code subspace. And these excitations are maximally, we are considering a state where this bulk mode is maximally entangled with a reference mode. Okay, so there's some qubit which is sitting out there outside the universe, and it's maximally entangled with this bulk mode. Okay, so this is the picture to have in mind. So now with this we can compute. So if I want to compute let's say I want to compute, let's say first this term, the entanglement entropy of A bar, what will I do? Well, I'm going to use the Ryu-Takayama formula. So this thing here is A over 4G Newton plus the bulk entanglement in the entanglement wedge of A bar, which is this region here. Right. And then for the entanglement of A, I again use the Ryu-Takayama formula. This is again A over 4G Newton plus the bulk entanglement in the entanglement wedge of A now. So in the shaded region. Okay. As you can see, the area terms cancel out. The bulk terms, so for the bulk terms, much of it will cancel out because the bulk is a pure state between A and A bar, the little a and little A bar, except for one thing, which is that there is this mode which is sitting around in the entanglement wedge of capital A. Okay. So from the point of view of A and A bar, this mode is maximally mixed because, if you're looking at the entanglement entropy of either A or A bar, you've traced out over the references. Okay, you've traced out over this guy. So in other words, it appears that this mode, which is sitting around in the bulk, is maximally mixed. Okay, it has maximal entanglement. Okay. since it is sitting in the entanglement wedge of capital A, let's consider that case first. If it's sitting in the entanglement wedge of capital A, it's going to contribute a log D to this thing here, the bulk entanglement entropy of little a. Okay, so this is where the log D is coming. This log D. It's coming from the fact that I have a maximally entangled or maximally mixed mode, which is sitting in the entanglement wedge of A, and it's contributing to this bulk entanglement. Okay. There are also other modes, of course, as you guys have pointed out. There's a QFT Hilbert space in the bulk. So there are other modes, and they also contribute to this bulk entanglement entropy, but they will cancel because the total state on little a bar, other than this mode, is essentially the vacuum state. So it's pure. So the entanglement entropy of little a will cancel with the entanglement entropy of little a bar, except for this one mode, which is in a maximally mixed state.
So, but sorry, this is what Alok was trying to ask earlier. Can you generalize this to an arbitrary effective field theory in AdS, where the same computation will go through somehow? Will that be true in this case, that this log, this S bulk A minus A bar will cancel the contribution of S psi?
You're saying in cases where this Hilbert space, you want to make the code subspace the Hilbert space of the bulk QFT
of an effective field theory, as you said,
of an effective field theory. I think so. I mean, as long as it's like, yeah, I think so. As long as it's finite dimensional, and you put some cutoffs and stuff, and you make it finite dimensional, then I think it should be fine. I don't see any immediate obstruction. I mean, in particular, there is no, so this code subspace dimension here doesn't have to be small. It can be any finite number.
No, but this cancellation has to happen even there, right? This SI has to. So is that known to be true, or I mean, is that guaranteed to?
Yeah, I suspect that it should work. I mean, my only intuition for this comes from Renyi entropy calculations. I'm not 100% sure that it's true, but I suspect that it should work. But I'm not 100% sure.
Okay, thanks.
Yeah. But at least in this sort of limited setting where you have a finite dimensional Hilbert space, where we're considering this kind of special code subspace. Yeah, the kind of problem that might happen with the setting that you want is that you might worry that. So one of the things that's special about the code subspace that are considered is that it's factorized between little a and little a. There's not much entanglement between little a and little a. I feel like, as long as your code subspace has that structure where you can consider low energy states which factorize between little a and little a bar, I think that much of this discussion will go through. As soon as you start considering states where factorized states have very high energy and they back react very strongly, I think the discussion breaks up. So that's really the obstruction here. The thing that you want to consider is you want to consider an EFT where you can consider factorized states which are of low energy. I think that is the main key requirement of this discussion.
Okay.
Yeah.
Thanks.
Onkar, I'm confused about the use of. So you want to construct a maximally entangled state between this A and its reference image, and but you have a particular wave packet in mind, psi.
Yes.
So you were constructing a little Hilbert space of operators acting on psi. What exactly? Okay, so what is D? This D is the dimension of what?
Right. So there's this wave packet mode in the bulk, and we use that to create excitations. So let's say I consider its ground state and the first excited state. That would be like the code subspace. If you can take the first excited state, second excited state, up to dth excited state. That would be the code subspace.
So what do you mean by excited state of the wave packet?
There's some.
Oh, you mean like instead of Gaussian, I could sort of start acting polynomials to, yeah, I see.
Yeah, exactly. So there's some creation operator associated to this wave packet. And I consider states of this.
Yeah. All right.
Yeah.
Okay, got it. Thanks.
Yeah.
And D, you are
up to D.
Up to D. Okay.
Yeah, up to D. Exactly.
Okay.
Yeah. Great. So, yeah.
Sorry, is there an invariant statement about this energy thing that because, for example, a dagger, I mean, in a different reference frame, they would have different energies.
You're asking about the energy criterion for when this effective field theory discussion breaks down.
Yeah.
Yeah, I don't know whether to. Yeah, I don't know whether there's an. I mean, maybe in terms of modular energy or something like that. Okay. I don't know whether there's an invariant discussion. That would be my first attempt. I mean, maybe you want to say something like, well, okay, I'm not sure. Let me not have that again. But okay. Roughly, the intuition is that as soon as you start considering states where factorized states have very high energy and back react strongly on the geometry, then you have to be careful.
Yeah. The situation I had in mind was something like we go to some AdS Rindler type thing where we have B dagger things, a different set of modes, but they are of course have contribution from all these A dagger modes. Some of them, even a low energy Rindler particle, have contribution from high energy Minkowski, or in this case AdS particles. So it's not. Yeah. So
right. But nevertheless, you can compute the stress tensor of the bulk field theory in these states, and you can check whether that stress tensor is small or not, right?
Yeah.
Whether it back reacts strongly or not. Yeah. That's I mean, maybe that's the most invariant thing one. Okay, good. So I hope that.
Sorry, Onkar, to slow you down. I mean,
no, go on.
Yeah, I think you already probably addressed this question. So the difference between S bulk A bar and S bulk A. So you say that that's log of D, where this D is the number of quanta that you have this wave packets that you have constructed. Is the A dagger. How many A daggers there are?
Yes.
How do I know this? How do I know this result?
Okay, so the intuitive way of, so first of all, you can try to get this by doing a Renyi entropy calculation, but intuitively the argument is this. See, in the entanglement entropy of capital A, the entanglement entropy of capital A is the area over 4G Newton term plus S bulk of the entanglement wedge of little a.
Yeah.
Right. Now there is this mode which is sitting around in this little a region, which is maximally mixed. Right? It's maximally mixed because in computing the entanglement entropy of capital A, you have traced out the reference system. Yes?
Nice.
So there is a mode which is sitting in the entanglement wedge of capital A, which is maximally mixed. So therefore, that mode is going to contribute a log D to this bulk entanglement entropy. Okay.
But, even if the bulk gravitons, the bulk quantum field theory of scalar fields or whatever, even if they were on their ground state,
absolutely,
you'd still have some contribution.
That's right. That's right. So there are other modes which are, of course, in their vacuum state, but the contribution of those modes would cancel out between these two terms. The ones I'm highlighting now. Note that there is an S bulk of A bar minus S bulk of A here, right?
Oh, I see.
So those modes which are sort of in their vacuum state and not excited will just cancel because those are in a pure state in the bulk.
Yeah, I see.
Okay.
So the only mixed nature comes because of the tracing of the differences.
Yes, exactly. So that's the only difference between these two terms. That's a log D. But now this log D will cancel with this log D and you'll get a 0.
Excellent. Got it. Thanks.
Okay. Just as an instructive thing, if this code subspace that we had considered was not in the entanglement wedge of A, but let's say that it was in the entanglement wedge of A bar. So let's say that this mode was here. Okay, and now this thing was maximally entangled with the reference. Now the calculation would be almost the same, except this log D, instead of being here, the log D would be here because this node is sitting in the entanglement wedge of A bar. And so then you would get a plus log D in this formula, and that would add up to 2 times log D. Okay.
Lovely.
So that says that when this bulk mode is in the entanglement wedge of capital A, it's protected against the erasure of capital A bar. But if the bulk mode was in the entanglement wedge of, was not in the entanglement wedge of capital A, then it would not be protected against the erasure of A bar. Okay. This is basically the statement of this is, if you like, in the Stoim model setting of like considering a wave packet and its excitations. This is the statement of quantum of why the Ryu-Takayanagi formula translates into quantum error correction.
Onkar?
Yes.
Sorry, can I ask one other question? So the cancellation of log D with log D seems like a very delicate thing where you had to make this extra assumption that you're only allowing up to D excitations, and it wouldn't work otherwise if you were allowing like more than D or less than D.
Sorry.
Packet.
No, why is that? Because the reference I'm going to consider is always going to be isomorphic to the code subspace. So the reference qubit and the bulk qubit always have the same dimension.
No, I mean the log D contribution was coming from the wave packet, right? And here
it's coming from the bulk entanglement. Yeah.
Yes. But that was an extra assumption that you're putting in, that you're allowing up to D excitations from the
if you allow D prime excitations, then the reference qubit that you would consider would also be D prime dimension.
Okay, yes. Thanks.
So they're always of the same dimension. So they it's either 0 or not 0. They either cancel or not cancel.
Yes. Thanks.
Okay. So I hope that I've at least tried to convince. I know that I'm out of time, but I hope that I've at least tried to convey to you why the Ryu-Takayanagi formula in AdS CFT translates into a statement of quantum error correction. I just wanted to highlight. I won't go through this in any detail, but let me just say that one of the things that I wanted to do, and I'll put up my notes so that in case this is of any use. One of the things that this is useful for, in case you're skeptical, is that you can use this quantum error correction perspective on the AdS CFT map to do bulk reconstruction. Of course, this was already explained in Hardlow's paper from 2016, but I wanted to emphasize that you can use this perspective. This is not just a theoretical curiosity. It's a useful one because you can use this quantum error correction perspective to do bulk reconstruction. Namely, you can use it to write down for explicit formulas for bulk operators in terms of boundary CFT operators, in particular going beyond things like HKLL and stuff like that. Unfortunately, I won't have the time to go through the details of that in this lecture. Some of this is in my notes. So if you want, you can, in your free time, you can take a look. Or of course, much of this is also explained in Hardlow's paper. So maybe this is a good point for me to stop. And if there are any further questions.
Okay, first let's thank Onkar for the excellent set of lectures. Thanks, Onkar.
Thank you for inviting me.
Now,
so yeah, Onkar, I had a question about the last. So as you explained that when you are doing from the quantum information side, that is mutual information vanishing is really like just telling you that the channel is recoverable, but to actually recover, we need the R.
Yes.
And so this to show that the bulk reconstruction can be obtained only from A and not about A bar, like going beyond HKLL, that would be like analog of constructing an R.
That's exactly analog of constructing an R. Yes, and you can do it. That's the point.
I see.
Yeah, that essentially you can do that. You can construct an R basically using this using the same kind of logic that we discussed in this Neal-Laflamme conditions discussion, and at least to a pretty good extent, write down formulas for boundary CFT operators, which will sort of reproduce bulk operators.
I see.
Yeah. So that gives you at least some technology to do this, going beyond HKML.
So can things like Papadodimas Raju proposal be understood also in terms of recovery channel operation?
I think so. I think that the PR proposal is probably closely related to this recovery channel way of thinking about things. But unfortunately, I have never like sorted through this myself. So maybe next week when you're here, Alok, we can have a discussion.
Yeah, I'll ask you more.
No. I mean, maybe we can try to jointly sort through this and see.
We'll discuss definitely.
That would be nice.
No, I see. But you know of any literature where people have asked this question? If those proposals,
I just know that there was one paper maybe 2 weeks back by Bahiru and one more person.
Oh, that recent. Okay.
I haven't. Unfortunately don't remember the name of his collaborator. It was Bahiru was one of the authors, I believe. No, sorry, not Bahiru. Sorry, sorry. So let me not name.
Yeah, okay. I'll ask you.
But there is a paper from 1 or 2 weeks ago where they try to explore this question. Yes.
There is also a 2018 paper by Roe Jefferson where they try to sort of show some comment on some relations between Papadodimas Raju proposal and the Almairi, Harlow, and those proposal of 2015.
Okay, that would also be very useful to look at. Thanks.
It's that I forgot the title. I think it's state dependence in something like comment on state dependence in bulk reconstruction.
Okay, that would be very thanks a lot. That would be very helpful to look at.
Onkar, in the here you showed basically one side of the equivalence between decoupling theorem and Ryutakenagi. So the other side is also straightforward.
The other side is also true. I mean, this is there in the lecture notes, but I didn't get to it. But yes, it's also true that if you can show the other way, which is that if this quantum error correction structure is satisfied, then there exists an analog of the Ryutakenagi quantum. That's also true. Yes, but unfortunately, I didn't get to it. Okay, so okay. So let me just echo the comments in the chat. I too agree. Thank you so much to the organizers for organizing this wonderful workshop.
So Nirmali, you want to say some last words before we end?
Yeah, I just want to say thank you to everyone for participating and making this a very successful workshop, much more than we had anticipated. We were worried that, first that it won't happen and then no one would turn up. But thanks to all the speakers and the participants and also my co-organizers who managed to overcome all my efforts to sabotage this thing. And we had a good time. I hope you all had a good time. So thanks again, and we will see you later.
Thank you, everyone. Bye.
Thank you.
Thanks
a lot, guys.
Bye.
Thanks, Onkar. See you next week. Bye.